morning, everyone. My name is Mingwei Zheng. Today, I'm going to introduce our recent work, ParDiff, which is a static differential analysis for network protocol parsers. And this work is done by me and the other collaborators from Purdue University. Before introducing our technique, let me first give some background about network protocol parsing. Network protocols are rules that allow devices to communicate, like the TLS protocol for secure communication, and the FTP protocol for file transfers, and the IP protocol for routing data. Network protocol parsing is a key step where incoming data is checked and broken down. This involves input validation, which checks whether the incoming data satisfies some correct format, and also the field extraction, which extracts some specific field value from the raw data. And once passed, the system uses the data for further processing, like transferring files or setting up a secure connection. Network protocol parsing bugs can lead to serious issues like security vulnerabilities or system miscommunications. Here is an example of the Xuwei bug in the bubble protocol detected by our tool. Bubble is a routing protocol exists in both wild and wilderness network, and it is used to find the best routing path for data transfer. Before diving into this bug, let's first understand the correct behavior when receiving a bubble packet. On the left, there is a valid bubble packet with update message, and it has a 2 bytes payload with a value 50. The packet is then sent to a server, and the server will store this packet in its buffer, and then it will copy the value 50 into a specific field channel. Finally, the server calls the update route function to update the routing table using this specific channel value. Now, let's see what should happen when the network packet is invalid. On the left, we have another update packet, which is also supposed to have a 2 byte payload. However, in this time, it is empty. So this is an invalid packet. And in this case, the server identifies that the packet is invalid and chooses to either report an error or just simply discard this packet from further processing. However, in the buggy location, in the buggy implementation, the server doesn't recognize the packet is invalid and continues to copy the 2 extra bytes, which is actually not inside the original network packet into the channel field. And this results in that the update route function is called with the incorrect channel value. So this is not a typical buff overread bug that can cause crashes. The incorrect channel value can lead to wrong routing decisions, potentially increasing the latency or causing any packet loss. And also, it may introduce some security risks. Attackers could exploit this to reroute some sensitive traffic through insecure channels. And so it's very important for the server to correctly parse and validate each packet before further processing and routing. Then let's take a look at the Xuwei implementation bug. On the right, you can see the packet structure. It has a field type, which is 1 byte, and another length field, which is also 1 byte, and additional channel field. And the length of the channel field is determined by the value of the length field, actually. And the total length size, we define it as packet length. And the packet length should include at least the size of the type field and the length field and also the channel field. So we need to guarantee that the value of the packet length is greater or equal to 1 plus 1 plus length. So it is packet length greater or equal to length plus 2. However, in the buggy code, it checks like in the red code line, it has a if checking if length greater than packet length and return error. So this means that the parser only guarantees that the packet length should be greater or equal to length instead of length plus 2. So this is actually incorrect. Just like the Xuwei bug we mentioned, many protocol parsing bugs are silent data corruptions, which violate protocol rules but don't crash the system. So traditional fuzzing techniques can often miss this kind of bugs. Model checkers, which need protocol-specific oral code to detect these bugs. But formal specifications are often missing since the network protocols are often described in natural language documents, such as the RFC documents. And so it's very time-consuming to manually construct those formal specifications in order to let model checkers to detect the bug. So the traditional testing tools fail to find this kind of silent bugs. Then how can we catch these silent bugs? We noticed that different platforms like FreeBSD, Linux, and also Windows, they have their own implementations of the same network protocols, such as the Bluetooth protocol. And these implementations are meant to provide the same functionality for the same network protocol. And this means that if we find any inconsistency in their parsing behavior, it might indicate some, at least inconsistency, but also it might indicate some bugs, right? So this time, we decided to use differential analysis to catch these silent bugs. However, existing static differential analysis often fails to catch the bugs inside syntactically disparate programs. So like the word GraphDiff and the differential symbolic execution, they work well in programs which are semantically very similar. The program looks very similar, syntactically similar programs. But when it comes to syntactically disparate programs, they may fail. And dynamic differential analysis, like the differential testing or differential fuzzing, works by running both implementation A and implementation B with the same input. And then if their execution behavior differs, it can reveal potential bugs. However, these techniques often require high-quality seed inputs to achieve high code coverage. So in the parsing code, to reach the buggy code, there might be a lot of parsing input validation check-ins before the buggy line. So the test case need to bypass all those input validation check-ins before reaching the buggy code. And this is actually very difficult because many validation check-ins in network protocol parsings are very complex. So this may lead to the missing of a lot of bugs. And another thing is that when differences are found, they don't directly point out where the buggy code is, and requires a lot of manual effort to check, okay, so where the buggy code is located inside the source code. So to address the limitations of existing differential analysis tools and also the traditional bug detection tools, we need a differential analysis technique that can handle syntactically disparate programs, and we also needed to achieve precise comparison and also offer no-effort bug localization. As we know, parser implementations implement protocol formats, and on the other hand, the protocol formats can also be inferred from the source code. This is done by collecting some parse constraints from successful parsing paths. And we can see an example for that. For the parser implementation on the left, there are two successful parsing paths, which actually return success in this case. And the first path, I highlighted it in yellow. It has if one greater or equal to packet length return error, so it requires packet length greater than 1. And also checking for the type field. The type field is actually representing the first byte in the buffer, so it requires the buffer at the first byte of the buffer be equal to 0 in order to return success. So we got the parse constraints on the right. The packet length should be greater than 1, and then packet 0 should be equal to 0 for this pass. Another successful parsing path, which is also highlighted in yellow this time, it requires packet length greater than 1 and packet 0 not equal to 0, and the packet 1 no greater than packet length. So the protocol formats for this parser is actually made up of the disjunctions of the two parse constraints derived from the source code implementation. And so by comparing the protocol formats from different implementations, we are able to find semantic differences between the parsers. So here is the basic idea of ParDiff. We extract proto formats from different implementations and compare these formats to find any inconsistencies. To discover the CV bug we described earlier, we get another implementation. And then we extract the format from both implementations. Since we represent the protocol formats in first-order logic formulas on Peki and Peki lengths, we can compare syntactically disparate programs by just simply comparing these two formulas. To compare the two formulas, it seems straightforward to use the SMT solver to check whether phi1 not equal to phi2 is satisfiable or not. And if satisfiable, the SMT solver can give us an input which can be passed by one implementation but failed by another. And this may indicate inconsistency here, right? However, in real-world cases, the format constraints are often very long and complex. The difference itself cannot directly pinpoint where the difference locates. So, and also, this only show one difference at a time between those two formulas. And if we want to, And if we want to get all possible differences, we may need to repeatedly query the SMT solver in order to catch more differences, which is actually very inefficient. So to compare the two formats precisely, ParDiff transforms its format into a finite state machine. State transitions in a finite state machine represent constraints on the input, and this is ordered by the buffer indices. For example, in the example here, we have both finite state machines start with constraint on packet length, and then followed by constraint on packet 0, and finally constraint on packet 1. Once the finite state machines are built, we use bisimulation to compare the two finite state machines. We start from the initial state as 0 and then recursively matching states. In the first finite state machine, the state transition starts from S0, and from S0 to S1, it requires constraint like packet length greater than 1. And for another finite state machine, from state 0 to state 1, we have packet length greater or equal to 2. And we give these two formulas into SMT solver and to check whether these formulas are equivalent or not. And here, obviously, it is equivalent. So we can match the two S1 states together. As we continue the bisimulation, we eventually find that the last S4 states cannot be matched. This is because that the state transition from S3 to S4, in one implementation, it requires packet 1 no greater than packet length, and another implementation requires packet 1 plus 2 no greater than packet length. So these two formulas are not equivalent, so we found an inconsistency here. This process allows us to match semantically equivalent constraints while also identify any inconsistencies. Our comparison is both precise and efficient by breaking down the comparison of the large and complex formulas like the phi1 and phi2 into multiple comparisons of these kind of small ones. Each inconsistency we get from the last step is a pair of constraints derived from the source code. And by maintaining a mapping from the source code checkings and the past constraints we derived, when we found the inconsistent here, we are able to trace back into a source code location where the buggy code occurs. So this makes bug localization much easier and low effort. ParDiff is built on top of LLVM, compiler infrastructure, and Z3 SMT solver. Although our current implementation mainly focuses on parsers implemented in C, the idea of ParDiff applies to parsers in all programming languages. We evaluate ParDiff with 14 protocols, and for each protocol, we select 2 different implementations for comparison. And it takes ParDiff an average of around 50 seconds to finish each protocol. And this includes lifting both formats from from two implementations and also transforming the formats into a finite state machine and also do bisimulation and the finite state machine. In total, ParDiff found 41 new bugs in real-world parser implementations and with a false positive rate of only 7%. So you can see ParDiff is quite efficient in bug finding. More technical details and evaluation results are available in our paper. So in summary, ParDiff is able to compile syntactically disparate programs by lifting formats from the implementation source code. And it achieves precise and fine-grained comparison by transforming format into finite state machines and then do bisimulation. Also, it provides low-effort bug localization. Thank you all for listening. Please feel free to scan the QR code if you are interested in our work. Thank you again.
So thank you for your great talk. I have a little bit of question about that. So first, since I think this workflow in general, it can work not only on the network protocol parsers, it can work on many basic systems, like you want to compare program A to program B, if they're equivalent. And second, for equivalent comparison, since we are using finite state machine, it can be viewed as a DFA. Have you considered other methods like linear algebra or some other methods? Thank you.
Sorry, can you repeat your question again?
Okay, the first question is that can your workflow push to other applications other than network protocol parsers?
Okay, let me first answer the first question. You mean that whether we can apply our ParDiff into more general testing frameworks, like we evaluate ParDiff in some other implementations. I think to this question, I think currently we are only able to handle the comparison of input validation check-ins because we are extracting the pass constraints, which is directly from the source code if-else checking or switch case checking. And these pass constraints, I think it is applies to those kind of parsing or input validation checking, not only to network protocol parsings, but also to the other applications like the media codecs or something. So I think this, the ParDiff can be applied to those implementations which have something related to input validation and parsing. So this is for your first question.
Okay, thank you for your answer. So the second question is that since you are comparing finite state machine, have you considered other methodologies to compare them, or why, if you consider, why you don't use them? Thank you.
I think finite state machine is just a data structure to used to breaking down the large formulas into small parts and for comparison. I think you do not need to consider finite machine as a totally different thing. It is just a different data structure representation of the past constraints. So I mean, for any other techniques, it may also use some other data structures to represent the formats in different ways. But the key idea should be very similar. It is still to do the comparison on the past constraints itself in different ways. I mean, yeah.
Thank you very much.
Thank you.
Yeah, thanks. This was really cool.
Thank you.
I have a bunch of questions. I'm trying to figure out which one to ask. So I'm a bit confused about the trend, about how you generate the finite state machines. It sounds like you generate them from this set of logical constraints, the format, which is, and then the finite state machine looked a lot like maybe an AST, a different notation of an AST. Is that a right way to think about it, with maybe some commutativity constraints as well? Or is there something else going on with how these finite state machines are like, can you have loops in these finite state machines?
I think in our state machine, we don't have loops. It is like, you can maybe take a look at the example here. It is more like, for the format, once we extract it from the source code, it may contain the check-ins on different byte of the input buffer. And the order might not be directly follow the buffer indices, right? So here we just do a reordering. I mean, so start from, we are based on this kind of assumptions, like if two formulas are equivalent, then it's check-ins on the packet length should be equivalent, and then its checkings on the packet 0 and the packet 1 should also be similar. So we did these finite machines to, before that, I think it is kind of reorder to make it follow the buffer indices, and then to kind of sort these path constraints and only compare the path constraints related to some specific field or specific byte indices. Yeah, this is what our finite machine do. And regarding to your loop, I think it does not exist here because, I mean, for the real world code, source code, we do the loop unrolling to handle different. I mean, there are a lot of while loops inside the parsing code, but it is supposed to provide the same semantic constraint on the input buffer. Yeah. So
I have a quick follow-up question, if that's okay.
We're actually running out of time, but
okay, I'll follow up later.
We can just make this discussion offline because it's fine.
Yeah, I think I will hold a OOPSLA session this night. So if you have any further question or any collaboration opportunities, I'm very happy to discuss that with you. Thank you all. Thanks.
Great.